Yes, thank you so much for the organizer for having me, and thank to you for listening in now. So we already had the spoiler, the teaser. Magnetic resonance imaging is my bread, and yes, thanks. Yes, this is, I guess, the reason. Because with a magnetic resonance imaging scanner, you can do so much things. Really, really a lot of things. And we will hear more about that this afternoon and in a couple of days. And this is what's so fascinating. But how does that work? It can sometimes be a bit confusing, and I hope that these slides will help you to dig into this. So what are we really looking at when we do MRI? Mainly we look at water. We also look a little bit at lipids, and we can see also, we can use spectroscopy to see some other elements as well, but usually when we sit at the MRI scanner and we do diagnostic work, we only use water. And this water, the history of the water, what it's doing inside there and how it interacts with the magnetic field and its own magnetic properties locally in that tissue, that's what determines what our images should look like. And therefore, I would claim that this water and its magnetic properties is a proxy for brain structure, also at the subvoxel level. You already heard yesterday that the beauty of water is that it has hydrogens on it, and the hydrogen has a nuclear spin with a total angular momentum, so it will tend to, at least on average, to align with this field. But not, of course, every water molecule will do that. Not every hydrogen will align with the field. We actually have a lot of water inside there, and all the hydrogens will resonate at the Larmor frequency, which is a very important thing in MRI to always be aware of. But the thing is that MRI has its downsides, and its main downside, I would say that it's slow, of course, but then this other thing, it's not very sensitive. We see about 5 out of 100,000 of these hydrogens at a magnetic field strength of 7 Tesla. So we cannot see many of them. What do we see then? Well, we cannot really see this either. So meaning that if you put a water bottle inside the scanner, you won't have any signal. Yeah, nothing happens. You will just have this splitting of the energy level, but you can't see anything. So therefore, we have to tickle it a little bit, and we tickle it by using a radio frequency pulse, which oscillates at the Larmor frequency so that it matches this energy gap, and that energy will be absorbed by the hydrogens of the water. And then, in that process, we create something called transverse magnetization. And in a way, this is my little personal view of this. This is not very quantum mechanically correct or anything. But what we're looking at is always this in between. This means that there are spins that are jumping between energy levels. We don't know, and we actually do not care so much, I think, well, most of the time. You will, in the inversion recovery, we will do. So we don't care too much about in which energy level it is, besides the fact that they are changing energy. So this is why I now introduce our little friend for today. It's a frog. And whenever you see this frog, you know that you can observe that magnetization. If it's not there, you cannot see it. So how can we then have this wide palette of different signals? Well, it does depend on the tissue properties, as I already listed some of them. Here are some more of them. But it also depends a lot what you do at the scanner. It depends in the very first place about the type of MR sequence that you will use. And you will encounter the inversion recovery today. We will have a look at the spin echo, and we will look at the gradient echo. Yeah? So that determines the main behavior of the hydrogen inside your measurement. It will also depend on how you how you change the settings of these sequences. So when you change the settings, you completely can change the type of signal that you observe. So this gives another degree of freedom for our measurements. So let's go to another representation of this net magnetization. And this is our rotating frame representation that we were just introduced. And you see here, in principle, after the RF frequency pulse, we can actually start observing the magnetization, because we have magnetization here in something we say in the transverse plane. So we have XY magnetization. It's no longer longitudinal. Longitudinal meaning that it's fixed in some of its energy level. Well, virtually fixed, net magnetization at least. So when we do that, the hydrogens will not behave very well, because they will, you can think of each hydrogen as little own magnets fluctuating around there. So when you say you have a static magnetic field in MRI, this is not really true, because you will have a lot of things happening at the voxel level. And that things that happen at the voxel level, this molecular tumbling of things, it will make these magnetization vectors to behave in different waves. And when we actually measure, when we actually observe this magnetization in the end, the signal we will get will depend on the vector sum of all these hydrogens in there. So during this, by changing a sequence parameter, which we know as the echo time, we can let these fluctuations evolve. We can observe them as they happen. And that gives us new contrast. There is another sequence parameter that you can look at, and that's the repetition time. That is the time that we leave the rotating frame magnetization vector in peace before we repeat the measurement. And here a little bit, I'm already alluding at it, it's slow. We really need to wait a long time to gain back the full magnetization vector, to have full equilibrium again and take account of to be able to measure the full magnetization again. We have to wait between two experiments in MRI 5 times the so-called T1 relaxation time. And this value here at 3 Tesla would be like 1.5 seconds in the brain. So you see here, and then we have to repeat that to get an image, and an image is 256 repetitions, between 64 and 256. So you see, everything is getting really slow if we respect this limit. So MR people usually don't respect that limit, but in principle, it's there. Okay, so we have the exactly the transverse magnetization, which we can observe, and we can observe how these interact. But we can also indirectly observe this T1 relaxation by applying some tricks. So we have a whole palette of different contrasts that we can get out, and these are the typical ones that you would see radiologists use. So it's a T1 weighted, a proton density weighted, it's a T2 weighted, and you see the images of the human brain here look quite different. And you can achieve these different weightings by just changing these sequence parameters, so echo times and repetition times. And these images would typically be done with spin echo sequences. And more about that later, because we will consider one more thing, because now I write crudely here, introduce to you something that I say is T1 relaxation and T2 relaxation, and you say, hey, what does that mean? And in order to do that, we need to do a little bit of maths. We need to look at the Bloch equations. And the Bloch equations, what do? They simply describe what happens with this magnetization vector that we have been looking at on average after taking the vector sum over time. So it's quite useful. So it's just a partial derivative equation here in time, and you see here I have already separated the longitudinal magnetization and the transverse magnetization. And you see the T1 time here only depends on the, only regulates, let's say, the longitudinal part, while T2 regulates the transverse part. So this is what we saw in the earlier slides. Okay, so how does it work? So we have the longitudinal magnetization, and when we change repetition time, when we shorten repetition time, we get a suppression of the signal. When we do an inversion recovery sequence, we get more and more signal with time. So we can indirectly measure the relaxation time, although we cannot observe this directly. Then we have this transverse magnetization, or the effective transverse magnetization. So we actually have two components here, as you will see in a bit. And they only interact with the transverse, or regulate the transverse magnetization, as you see here. And what they have is that you actually lose signal here, so you have a T2 decay, or T2 star decay in MRI. Then we have an extra bit here. These are these additional local magnetic fields. And we can put a lot in here. We can put the RF excitation, we can put the spatial encoding, whatnot. But in terms of MR contrast, we are more interested in this guy here, the magnetic susceptibility. Because we can, the magnetic susceptibility, the little additional change in Larmor frequency in the order of 0.2 ppm or something like that, actually changes the Larmor frequency. So we have a little bit of change in the B field, and we can investigate that as well. And you see here, this is a linear evolution in time. So we have these exponential evolutions in times and linear evolution in times that we can look at using MRI. Okay, so let's just go through these three bits now. We start with T1 and this inversion recovery sequence. An inversion recovery sequence is called like that because we use a 180-degree pulse, which inverts the spin. So this is a spin population inversion, and you get more spins in the higher energy state, which we called -1, actually -half, actually. This means that the spins here won't like to stay there. They will try to go back to equilibrium. The thing is, do you remember that little frog? Can we observe this phenomenon? I would like now a chorus. No, you can't, because we don't have the frog, right? So let's put the frog in. And so we need, it doesn't suffice to do this inversion pulse. We also need that little extra pulse to actually, the excitation pulse, to actually be able to observe it. So the longitudinal magnetization we never can observe, only the transverse one. So we can do that, right? So let's do some imaging, and this is a little bit what it looks like. So for each experiment now, we prolong the inversion time. So we wait more and more time between the inversion pulse and the excitation pulse. And when we do that, you can see here quite beautifully how the contrast between gray matter and white matter and cerebrospinal fluid in the brain changes. Yeah? And they have different recovery curves. White matter, and which is myelin, and gray matter, which is cortex. So we could actually repeat this measurement several times and fit that recovery curve, and this is then what we would see. We would see a lovely T1 histogram with white matter, the myelinated connections, having very short T1 times, and gray matter having longer T1 times, and cerebrospinal fluid having even more longer T1 times. And this generates contrasts both for quantitative mapping and for these weighted mappings, and it can actually be quite useful to quantify these things. So this is definitely a workhorse, this T1 weighted MRI. Also because when you put a contrast agent in your patient, what happens then is that this T1 will actually be shortened because there are paramagnetic contrast agents, so it will be shortened even more. So it's helpful for the clinicians to see where pathology resides. You can also do other things with it. If you use some kind of inversion recovery technique, you can start to do image segmentation. So you can separate gray matter, white matter, CSF, and then you can start to do morphometry, computational neuroanatomy, these kinds of things. You can also use quantitative T1 mapping. And why is that so interesting? It allows us to look at the myelin in the cortex. So this shows basically where the myelin should reside, and these are actual measurements of the T1 time in the brain of several subjects which have been averaged. And you see that where we expect the myelin to be thick, so a lot of very well insulated axonal connections in your brain, then T1, actually these are R1 images, it's high. Yeah? So R1 is just the inverse of T1, and we use them typically interchangeably. We can also use T1 weighted MRI to speed things up, and this is an important thing in MRI. So we just don't weight these 5 times the T1 time. We just make a shorter repetition time. We use small flip angles, so just tip it a little bit, and then we can speed things up. But we can do also more things. We can look on those water molecules which didn't sense the excitation pulse. And when we do that, we can look at moving spins, like in these blood vessels here. So here you can suppress parts of the signal and enrich, because they only sensed this excitation once, other parts of the brain. Another way of having contrast. Okay, so what do people do when they do this segmentation, computational neuroanatomy? Well, this is, I guess, what they will typically do. They would just acquire this image here with a decently high resolution, and then they will segment it. There are a lot of tools for that, free surfer, voxel-based morphometry, and then you can start to look actually at the surface of the brain too. So you can look at cortical thickness, quite popular. You can look at how the brain is folded, so you can study folding patterns with it. You can do a lot of fun things. And in Tübingen, people have been doing that at 9.4 Tesla as well, because this is the field strength that we work with there. And you can see here, you can press the voxel size a bit higher because you have more signal at higher field. So you can go down to 0.5 millimeter or so, and this is an atlas for that use. You can also use it to do some ex vivo scans. And here is actually an histogram here of the cortical thickness in different states, let's say. You can also use it for some clinical applications. So you can say, okay, how thick is the apparently the cortical thickness in focal dysplasia? So focal dysplasia is a type of epilepsy where you are not capable of actually finding the spot which causes this epileptic seizures of these patients. And after some time, these patients cannot longer be treated with pharmacologically, and that's an issue. So if you can localize this spot, you can actually go in and surgically remove that source, which then helps these patients. But what if you cannot even see it with MRI, this little spot? And you cannot see it with EEG. You cannot see it with any method. Well, this is what my colleagues have been working at. They have been working both at 3 Tesla, at 9.4 Tesla, and here are some examples from 3 Tesla, and you see the workhorse clinical images here, MP-RAGE and fluid attenuated inversion recovery techniques. And you can see here that actually some techniques work quite good in localizing the actual source of these epileptic foci. Now let's switch from T1 weighted imaging to T2 weighted imaging and quantification of T2 relaxation. And to do that, you will see something which you may have seen already yesterday, the magnetic resonance phenomena, right? We always look at these images and say, oh, this is the MRI. But really what we're looking at is always this resonance. We tend to forget that sometimes. And what's about this resonance? Okay, we know that it's happening at the Larmor frequency, but what actually caused these relaxation? What is the relaxation mechanisms? And they're actually similar for T1 and T2, but T2 has one extra relaxation mechanism. So T2 will always be shorter than T1, which is actually bad news, right? Because we had this decay, yeah? So we had to wait a long time in order to regain the full longitudinal magnetization. But we need to be really fast to acquire the signal because of this signal dephasing that T2 interactions cause. So you can think about it a little bit like this. We have this water hydrogens, they're all fluctuating in there, and they tumble around, so they don't tell the same story, so to say, and this will cause a certain broadening of this peak. And this is basically what we measure, what we look at when we do T2 relaxation. So how can it then be that we can see some contrast? Well, it's because some tissue actually have more effects of these fluctuations because they're fluctuating a bit less. Yeah? So you would have these water molecules which are trapped in the myelin membrane, for instance. So therefore, these interaction mechanisms of the magnetic properties can play out much better, and you get a broadening of your resonance peak. And then you have a shorter T2 effect. So where do we use this kind of T2 imaging? Well, it's very, very popular in the clinic. And you can actually get both information about T2 and information about proton density by just varying your sequence parameter. What we will see in a while is that you can actually start to determine what's the fraction of water that we have trapped inside the myelin. And that's myelin water fraction imaging. And then we can do something which people like a lot with MRI. It's diffusion-weighted MRI. So let's have a look at that. Because both these techniques, they are based on this sequence, the spin echo sequence. So you see here, now the 180-degree pulse is no longer before the excitation pulse. This is the excitation pulse. It's after. And we don't call it inversion pulse anymore. We call it refocusing pulse. So it's the same number, but it has a completely different meaning because it now acts in the transverse plane, no longer in the longitudinal plane as in the inversion recovery technique. So what do? We apply this 180-degree pulse after a certain time that we wait. It's half the echo time. And as our water does not always stay bravely here on resonance along the y direction, they will start to walk, apparently walk away from each other. So one will move clockwise, the other one will move anti-clockwise. We apply this 180-degree pulse, but they won't have noticed that they have been turned around, so the one which walked anti-clockwise will still do that. And in the end, they will come together. We just have to wait another echo time. So let's have a look at the signal. Here, you see that the signal disappears. This is due to dephasing. So you can imagine Erwin Hahn, when he did this experiment in the 50s, he put this 180-degree pulse in here, and suddenly the signal came back. So clearly these magnetic properties are really, really interesting because there are both reversible and irreversible processes that you can study. And the 180-degree pulse, they bring back all the reversible effects. And all the reversible effects, they are those related to local field inhomogeneities, broadly speaking, while the ones that we cannot reverse, they are caused by interactions at the molecular level. Okay, how does these images look like? Here's an example of a glioma patient. Gliomas come from glial cells, so white matter cells, let's say. They grow really, really fast, and you can see by changing the echo time, you can then change how well we can identify the borders of this tumor. But we can do more than so. We can start to look at pools of water which reside inside our voxels, because if you look at these myelinated fibers, they will have different pools. So you can start looking at this myelin water, which has a shortened T2 than the extra and intracellular water. And you do that typically by using this kind of techniques, and this is simply several echoes. And we have generated these several echoes by applying 180-degree pulse at several times after the excitation pulse. And when we do that, we see the typical T2 decay with increasing echo time. But actually inside this decay here, we have two components which are hidden. How can we tell them apart? There's a very nice trick. We do the inverse Laplace transform on it. When we do that, we can actually start separating these components residing here. B exponential fitting, as you may know, is really a nightmare. But by doing like this, we can quite elegantly just separate the two pools. Thing is that these pools exchange with each other. So exchange MRI is, of course, also a very, very hot topic, which I won't talk about. But it basically resides on this cartoon here. So depending on whether the exchange is fast or slow, you can or cannot observe the two pools. And depending on the time of it, you can discern between these pools more or less easily. So it's not completely straightforward to separate between these pools. And you can see also, depending on the pool size, you can also get funny effects here. But if you don't care about that, okay, I don't care about the exact T2 times. If you just say, okay, I want to see how big is this fraction, so the fraction of water which has short T2 times compared to the sum, then you can do these beautiful maps which are known as myelin water fraction images. And they are very, very helpful for characterizing white matter structures, as you can see here. So wherever the myelin is thicker, like here, the fibers that connect our motor cortex to the rest of our body, it will be thick and you will have high values. And this has been validated also in the literature. So why do we like this thing? Well, because, for instance, in this case, we have something that the clinicians called pseudonormalization in clinical MRI. That meant basically that they took the typical T1 and T2 weighted imaging. They looked at children with metachromatic leukodystrophy. That basically means that their myelin is breaking down because they're missing an important enzyme, so they cannot repair it and make it work nicely. But after some time, you cannot really see a good clinically clinical effect anymore. So we should have seen some bright spots here in the middle, and we don't. Yeah, and thing is that it's pretty hard to see with spectroscopy also, as a matter of fact, and the fluid attenuated inversion recovery sequences also didn't help the clinician a lot. But the nice thing was that myelin water fraction imaging did, and also another technique called magnetization transfer resonance. Other techniques that were quite helpful were based on diffusion MRI. So let's have a closer look at diffusion MRI, because to do that, we just simply use the same spin echo technique that you have already seen. But with one modification. So this is 90-degree pulse, 180-degree pulse. Yeah, we know that there is that there are dephasing going on, and that these dephasing, they are reversible, so we can get back our full signal in the end. And what we do is that we exasperate the system in some kind of way because we apply additional magnetic field to dephase these spins even more. So we dephase them really much, but after the 180-degree pulse, we rephase them again with a gradient of the same polarity. So this works very, very well because we will keep our signal unchanged if the water didn't move in between the two gradients. But if they actually moved, we will not be able to refocus the signal again. So we have less signal due to diffusion. And this is the diffusion phenomena, and the signal simply decays monoexponentially as we increase the strength and the duration of these diffusion sensitizing gradients. And we can actually look at different components by this. So we can, by using very long and strong diffusion gradients, we can look at really fast diffusion processes. And that means that the water will sense the borders put there by the cell membranes or the myelin or the reduced space inside the cells. But we can also look at free diffusion, so the surface to volume ratio, by using smaller gradients. So this is also a technique which you can do a lot of things with. My colleagues in Tübingen, they used it to look at something else. They look at this hindered diffusion, or this restricted diffusion. It was restricted so much in some places that they could start using it clinically. And what they evaluated was something which is called the mean kurtosis, which is basically the deviation from a monoexponential decay of this diffusion decay that you saw before. And what they did then is that they did MRI. So this is a T1 weighted MRI, and they have actually given a contrast agent to this patient. And by giving that contrast agent, wherever the blood-brain barrier is ruptured, the contrast agent can go inside the brain and shorten the T1. So then in a T1 weighted image, the signal would get very, very bright. And you see that that happens in all these places where the tumor still can grow a lot, because in the center of this tumor, there will likely be necrosis. There is no nutrition's coming in anymore, but at the borders of this tumor, it's still sitting there and wants to grow. And this is what you can see by giving contrast agent. And what Uwe Klose and his co-workers did was that they evaluated the kurtosis and the apparent diffusion coefficient at different distances from this tumor. And they had a look at different kinds of tumors, so glioblastoma, astrocytoma, oligodendroglioma, and they could see that the mean kurtosis actually deviated quite drastically and was more localized in that sense than the remainder of the tumors, which we know grow in a more infiltrative way. So that can be helpful. You can also use diffusion-weighted imaging to do some neuroscience, and this is what Svenja Brot in Tübingen did. She made her volunteers learn things, and she investigated them with diffusion-weighted imaging at only 90 minutes after learning and 12 hours after learning. And what you can see here is that you have a reduction in the mean diffusivity, or the apparent diffusion coefficient, due to this learning. And that can be due to astrocyte swelling, or it can be due to myelinization process is a bit fast, but actually people don't know why this happens. So this is an effect under study, but they were quite happy because they could show like this that memory is stored as images of what happened, let's say, as engrams in different parts of the brain, not only in the hippocampus, but also in those areas of the brain where sensory perception is mapped quite early in the process. Okay, so let's now move on from the spin echo to the next sequence. And before doing that, let's look at this situation. You see, I've put something in here. It says biometal. What could a biometal be in the body? What is it that you really need? Iron, yes, you need iron. So a biometal is iron, and iron is actually paramagnetic. And it's a natural paramagnetic product, and we can use that for MR contrast. So it can act in two ways. It can act either indirectly in time, by just making this dephasing process faster, and you can get broader peaks. But it can also act directly in space by changing the local magnetic field. And that's magnetic susceptibility. And that causes a shift in the frequency peak. And we can still detect this shift. Also with imaging, without looking at the resonance. It's kind of magic, but it kind of works. And how do we do it? Well, we need this other sequence. We need the gradient echo. And as you see, it's much easier, right? It's just an excitation pulse, and then we look at it. So we don't care about refocusing, reversible, irreversible. We don't care about manipulating the longitudinal relaxation or anything. It's really the most simple technique of them all, but maybe then what you then get out of it is a bit complicated. And what you look at is still kind of an echo here, so we call it an echo because we again exasperate our system. We dephase a lot, but we rephase it again, and as you see here, we change the polarity, and we have to change the polarity to dephase and rephase the spins again because we didn't put a 180-degree pulse in here anymore. So we actually need this polarity change to make any signal at all that we are able to see. And what happens then? You still have these guys that travel anti-clockwise and clockwise. But what happens now is that they won't go back together. Yeah? So they will continue to move apart, so in the sense that they do not change position here because we didn't have the 180-degree pulse. So some of this dephasing will be kept. Yeah? So we do have an echo, so we do have a rephasing, but we don't rephase the local effects in the tissue. Yeah? Sounds a bit wacko, but it's a little bit like this. Yeah? So we still have this part in the end of the images. So, but okay, it's an echo. I'm not convinced, you'd say, so let's have a closer look. So here you see two images obtained with the same, similar echo times or matched echo times, let's say. We have on one part the spin echo, and the other part the gradient echo. Are they the same? Can you see any differences? Let's zoom in. You can, right? Wherever you have iron, that is blood. So the blood becomes much more visible in the gradient echo than in the spin echo, because here we keep these reversible processes. Here we have reversed them, but here they're still in there. And these reversibly processes that we could choose to reverse, sometimes we choose not to. And this is the gradient echo. And what can I do? Yes, I still have this dependence on T2 when we do this kind of effective transverse relaxation mapping. But we have this extra bit here. That's caused by local field inhomogeneities. And you can see it directly here. This is an R2 star map. This is a true R2 map, so T2 map. And if we just subtract them from the other, we can actually see the local magnetic field deviations. And you have a lot where you have big vessels, so a lot of blood, but you also have a lot in some parts of the brain where you have a lot of iron. So this is a good way of mapping iron. But you can do more with it. You can do functional MRI. This is what typically effect you would also do when you do functional MRI. And you can also detect own storages of iron in the brain with this technique. But what's really fun with it is that you can not only look at this signal in the end, which is kind of the superposition of all these different components, and get the T2 star weighted image. So no, not the T2 weighted image, but the T2 star weighted image. You can do more. You can actually let these frequency differences evolve with the echo time. And if you do that, and you look at the phase signal, you will see that the phase evolves linearly with echo time due to these local field inhomogeneities, and you can generate images which are known as phase. They are also called phase contrast. There are other phase contrast images in MRI, but this is one type. And you see there are quite fun effects here where we have a lot of myelinated axons, but also where we have a lot of iron. So the thing is that these effects caused by magnetic susceptibility, they are non-local. So they are not only in the place where you have iron. You also have these field deviations outside where the iron are. And that is due to this dipolar nature of the magnetic field. The nice thing is that you can actually invert this, and some work with people from Marseille has also contributed a lot to this field. So you can take this map and you can invert it, and voila, you get something called quantitative susceptibility mapping. And that is a very, very nice technique, because we know from a very long time that the brain tends to accumulate iron. So we need it to do myelin, and we need it for a lot of things, to do good blood, etc., but we cannot get rid of it. So with increasing age, it does stop at some time. Yeah? It tends to plateau out, but it accumulates iron differently in different brain regions. And so if you measure a person, this is not the same person, but if you measure a person with different ages, you will see that in this case it gets darker and darker and darker, and that is because this magnetic, local magnetic susceptibility increases and increases. And you can actually do more. You can combine the information in different parts of the brain where you know that the iron content will be change, and you can estimate the molar susceptibility value for the brain. And then you can actually use some other techniques to verify that this is really the effect of iron, and you can verify that your technique is good enough, and things like this by using phantoms which have some iron inclusions. And then you can develop other techniques. You can say, okay, I'm not perhaps only interested in this molar susceptibility effects. Maybe I would like to know where these clusters are in space. How could we do that? Well, you can look at the histograms of these QSM values, and you can start doing cut-offs at different points of these histograms. And if you do that, you can actually estimate how many clusters you have, so some kind of a cluster load in each voxel. And by doing that, you have some kind, an iron load effect. And there is something in the clinic which tends to cluster iron, and that's Alzheimer's plaques. So Alzheimer's plaques, even if you have them in the test, if you have beta amyloid in a test tube, it will start to capture iron and bind it. And therefore, if you look on an Alzheimer's patient and control, the QSM values will be much higher, and the R2 star too. And if we now apply this little technique by this histogram technique, we can actually determine an apparent amyloid beta load for these patients. It works a little bit better at high field ex vivo than in vivo, but it's a possibility. Another possibility for using quantitative susceptibility maps, or a cousin of that technique, which is called susceptibility weighted imaging, where you combine basically the magnitude and the phase signal. You can see this in this patient with an enzymatic mutation. You can see local places where you have iron accumulation. And that can be helpful for the clinicians to make a diagnosis without having to do the genetic mapping. So let me conclude. Let me conclude now with a study which was actually done by Angela Osenberg. She was a master student in my lab during the past year. And what she did was to have a look at subjects who had been measured at 9.4 Tesla, where we did all these techniques. So we did mapping of T1. So 1 over T1 is R1. We did mapping of the effective transverse relaxation time. So 1 over T2 star is R2 star. And then we had also quantitative susceptibility maps for these subjects. And so we used also segmentation techniques to look at different cortical layers here. And the idea here was to find out if the age somehow influences the cortical layer profiles in here. And if we can capture those changes at 9.4 Tesla using box sizes between 400 and 800 micron. So these are the average maps. So you see there are some issues here because some parts of the brain were actually missing for R2 star and QSM. You can recognize this myelin typical pattern in most techniques very, very clearly in the R1 mapping, but also a little bit in the R2 star mapping. And the QSM, which then actually separates between contributions that are known, come from myelin and from iron, the patterns look a bit more wild. And when we go in here and look at different age cohorts, so group 1 is the youngest age cohort and group 4 is the oldest. So the youngest were around 20 and the oldest were about around 70. We can see that there are age differences. And specifically, there are age differences in brain regions which we know myelinate early in development and those which myelinate late in development. So let's say things that we myelinate perhaps during the entire course of our life, you can still observe it. So for instance, you could see here in the mid layer of the cortex, we could see myelinating effects, so more myelin in the older group than in the younger group. With R2 star, we could also see increases in R2 star, and they were located just close to the border between the cortex and the surrounding white matter. We also could see a shift in these QSM maxima, the most paramagnetic effect, towards the mid layers in these patient cohorts, suggestive of some myelination processes going on for a long time, at least. Okay, so in conclusion now, I hope that you have been convinced that we have a longitudinal magnetization component and that we have a transverse magnetization component and that we cannot observe this longitudinal component directly. We need excitation pulses in order to observe them. But we can still manipulate this longitudinal magnetization to measure T1 recovery by varying the inversion time. And that we can, in the transfer, for the transverse magnetization, study this on-resonance component, so changes in irreversible processes happening at the molecular level in a spin echo, and looking at phase accumulation effects in a gradient echo and do quantitative MRI of magnetic susceptibility. So we can look on these things that you have seen here at the beginning. Okay, I think this was everything I had today, and thank you so much for your attention, and you're very, very welcome with questions.